Now, previously, we looked at the Clausius statement for the second law of thermodynamics, which limited the efficiency of an engine. And basically, with a heat engine, you could never get all of the heat flowing from the hot reservoir to be producing 100% work. Now we're going to take a look at another statement of the second law, and this is known as the Kelvin statement, sometimes known as the Kelvin-Planck statement. And this is basically how it works and how we get our maximum efficiency. So once again, we can't ever have a 100% efficient engine because we can't directly turn all of QH into W. That just will not happen. Some of the energy is going to have to be exhausted into the cold reservoir. So some energy must be lost in the form of waste heat. So again, no engine operating between these two reservoirs will ever produce 100% work. Thus, the efficiency is going to be less than 1. But it also prevents a perfect refrigerator where no work is done, okay? So a heat engine, we say, is sort of the reverse of a refrigerator. Here in the first case, we have our 100% efficient heat engine, okay? This cannot happen because it would mean that all the heat, 100% of the heat, QH, has become work, okay? Theoretically, this could happen if you cool the temperature of the cold reservoir down to 0 degrees Kelvin, to absolute 0. But we'll see later on that another aspect of the second law of another law of thermodynamics, the third law of thermodynamics, actually prevents this. So we can never say that TC is ever going to be equal to 0. So again, this maximum efficiency, we're not going to be able to achieve that. Okay. Now on the other side, the cousin to the perfect heat engine would be the perfect refrigerator. Okay. Whereas we got 100% work out of all of the input energy, here, since the coefficient of performance is equal to either QC or QH over W, here we would say the work would be 0, okay? And that the heat would just naturally flow from the cold reservoir to the hot reservoir, which we know, in fact, can't happen, okay? So again, another obvious result of the second law of thermodynamics is you can't have a perfect heat engine, you can't have a perfect refrigerator. Now, one can imagine, let's say that if we could have a perfect refrigerator, okay, we could operate this with no consequences, with no increase in entropy. Remember before we talked about the fact that if we have a finite hot reservoir, that as we operate it, the temperature is going to go down. And if we have a finite cold reservoir, as we operate it, the temperature is going to go up. And eventually what will happen is the temperature of the two reservoirs will reach equilibrium and we won't be able to extract energy from this anymore. Okay, let's now introduce our magic perfect refrigerator and operate it between these two reservoirs so we can extract as much energy as we want, okay? Now, over on the right-hand side, I just have a normal heat engine, okay? And as I operate this heat engine, I get work out, and I know that's going to drop the temperature of the hot reservoir while increasing the temperature of the cold reservoir. But now my perfect refrigerator can offset that change in entropy. So whereas on the right side, okay, oh, come on, let me undo that. Whereas on the right side, at best, entropy is staying the same or entropy is increasing. On the left side, my perfect refrigerator is violating the second law of thermodynamics and it's dropping the entropy, okay? So any temperature decrease caused by the engine in the hot reservoir or any temperature increase caused by the engine in the cold reservoir is going to be offset by transferring that energy back into my hot reservoir, okay? That this Q right here, this QC, is simply going to be pumped back up to the hot reservoir without using any work, okay? So clearly, we can see that no engine can be 100% efficient and no refrigerator can operate such that its coefficient of performance would be infinite. And why do I say infinite? Because again, Q divided by W is the coefficient of performance. And if W is 0, this goes to infinity. Okay? All right. Now, within the Kelvin statements, there are two consequences. Okay? One, all reversible engines operating between two reservoirs have a greater efficiency than any irreversible engine. Okay? So what this is basically saying is, okay, in a perfectly reversible system, remember we said that nothing is perfectly reversible, that turbulence, friction, all these other things are going to make any of the processes slightly irreversible. But if we had two reversible engines operating across two reservoirs, they would have a greater efficiency than any irreversible engines. And that makes sense, right? Because irreversible engines, with their turbulence, with their friction, with their unequal temperatures, okay, they are all going to experience some energy loss and thus a decrease in efficiency. Okay, so again, this is sort of magic. Our reversible engines don't necessarily really exist, but if they did, they would be the most efficient engines possible. This is going to be very important for when we talk about the Carnot engines. Also, all reversible engines operating between the same two reservoirs with the same high temperature and cold temperature must have the same efficiency. Okay? This is why. All right? This isn't the greatest proof in the world, but this is as close as we can get to it. We know that efficiency is equal to the amount of work that I get out divided by the energy I get from the hot reservoir. Okay? So let's say that I have two engines operating. I have engine A over here, I have engine B over here. They're both operating between two reservoirs. Okay? Now, according to this, both of their efficiencies are going to be the same. All right? Now, if I suddenly was able to take heat engine B and reverse it, okay, having the same efficiency as A, it would operate in the reverse direction with the same consequences, which means I would have A operating, taking out, let me change colors because that's a little bit difficult to see there. I'd have A operating with QH coming out, okay? Some of that would be converted into work, W. Some of that would be converted into QC. The work would be then input into this engine right here, okay? And draw up the same amount of heat, because again, I'm operating in reverse, same amount of heat that I had to dump from A, and combining that, I would have the same QH, okay? So again, if they're perfectly reversible, okay? A heat engine that's perfectly reversible can act as a heat pump, okay? And essentially, being reversible, we can return to the original state. The reverse effect will completely reverse what the first one does. Thus, we must have the same efficiency, okay? Why do we even care about this? Well, because later on, we are going to look at what Carnot did, and he calculated the maximum efficiency of any heat engine. And what he discovered was that the maximum efficiency happens when he combines 4 reversible processes together, 2 adiabatic, 2 isothermal. And what he found is that this maximum efficiency goes by 1 minus TC over TA, 1 minus TC over TH. Okay? That all reversible engines will achieve this Carnot efficiency, whereas real engines have to be less than this and have to have a lower efficiency than the Carnot efficiency. Okay? So again, this will be important because it'll tell us for a given operating temperature how good the best engine could actually be. Okay?